Welcome. This is Dr. Michio Kaku, Professor of Theoretical Physics at the City College and the Graduate Center of the City University of New York, and this is Exploration. Every week on Exploration, we discuss the fascinating world of science and its impact on society. And today, once again, we're going to answer emails. I get hundreds of emails, and of course, it's impossible for me to answer all of them. And so instead, I'm going to try to answer some of these emails on air. Well, let's just jump right into some of the emails that I get. The first one concerns, well, it's been making headlines around the world. A lot of people are asking, how significant is this discovery of Proxima B, the closest planet to the Earth that resembles the planet Earth? Well, this is a dream come true. Astronomers spend their entire life waiting for a breakthrough of this magnitude, and this time astronomers hit the jackpot. They found a planet 30% bigger than our own planet Earth that is revolving around the closest star to the solar system, and that is Proxima Centauri. It's a triple star system. We have Alpha Centauri A, Alpha Centauri B, which form a binary star system with the two stars chasing each other. And then we have a much smaller third star, a companion, a red dwarf called Proxima Centauri, which is revolving around Alpha Centauri A and B. Now we find that if you zero in your telescopes based in Chile, to Proxima Centauri, you find that it has a solar system going around it. And Proxima B seems to have a planet that is right out of your dreams. It's a planet that is basically a doppelganger of the planet Earth. 30% bigger and just right from the mother star. In other words, if your planet is too close to the mother star, your oceans will boil. If you're too far away, the oceans will freeze. You want to be in the so-called Goldilocks zone where you are just right, not too hot, not too cold, but just right to have liquid water oceans, because liquid water is a universal solvent. It dissolves most substances besides certain oils and minerals, and it is the amniotic fluid out of which DNA and life first got off the ground. And so, after months of careful observation, bingo, astronomers announced that this planet, Proxima B, in fact, is the closest exoplanet to the planet Earth. Now, let's put this into perspective. If you look at the night sky, a typical star chosen at random in the night sky is several hundred to several thousand light years away. So you're looking at the star not as it is, but as it was several hundred to several thousand years ago when light was first emitted from that star. Now, this planet is only 4.2 light years away in comparison to the hundreds, thousands of light years that we find for most other stars. In other words, this planet is literally a hop, skip, and a jump away. Now, we should also point out that scientists have identified 20 doppelgangers of the planet Earth in outer space out of the 4,000 planets that have been looked at, analyzed, and documented by the Kepler telescope and by individual astronomers, almost 4,000 exoplanets. Of them, 20 look very much like the planet Earth. One of them, for example, is Kepler 186f. Kepler 186f also looks very much like the Earth. It's only 30% bigger. However, it is 500 light years from the planet Earth. Much too far to even envision sending a spacecraft in the near future. And then the next question is, well, if we have these 20 Earth-like candidates, one of which is just practically in our backyard, then when might we send the first probes? Well, most of us, of course, have this image of the Starship Enterprise, a gigantic starship containing hundreds of crew members zipping along across the galaxy. Well, such a starship is perhaps centuries, maybe thousands of years into the future. The technology to create an enterprise is simply not for us. However, as I've reported on Exploration, Stephen Hawking, as well as billionaires like Yuri Milner and Mark Zuckerberg of Facebook, have proposed another quick and dirty way to go to the nearby stars. This process involves using a bank of laser beams to the tune of 800 megawatts to shoot tiny postage stamp-sized chips to the nearest stars. Now think about how Mother Nature propagates life in the form of trees. Trees have seeds, tiny little seeds, most of which go nowhere. Most of the seeds simply die off and wither. However, a tiny fraction of these seeds are dispersed into the environment, and some of them take root and become trees. In the same way, Hawking et al. Envision sending maybe 1,000 postage stamp chips full of high-tech wizardry, sufficient for maybe a handful of them to actually make it to the Alpha Centauri system. Now, on that chip, you would have, of course, an onboard computer, you would have a telescope, you would have a radio, you would have a power supply system, all sorts of gadgets that you normally find in a starship compressed down to the size of a postage stamp. Now, what's the catch? It sounds like a great idea, basically a solar sail riding on a tidal wave of laser light, traveling at maybe 20% of the speed of light. Now, this is incredible. This means that you could probably reach Proxima B within 20 years. So let's put this into a time frame. The time frame is that perhaps in the next 20 to 30 years, these billionaires will amass enough money to build a system. Already, they have $100 million pledged toward building this spacecraft. Then they're going to build it. That is, they're going to build a bank of laser cannons sufficient to shoot 800 megawatts of laser power into outer space. Each of these chips has a parachute which then unfolds and grabs some of the laser light and then is accelerated 20% of the speed of light, reaching Proxima B perhaps within just a 20-year time frame. Already 100 million have been pledged for the project, mainly for research purposes, but perhaps by the end of the century, this may become commonplace. In fact, people are saying that if you can shoot this device to Alpha Centauri, then certainly you can shoot it to Mars. In fact, instead of having to wait years to go to Mars, you might be able to send these chips to Mars within a matter of days. Think of this. This could revolutionize space travel within our solar system, being able to send information in the form of chips, telescopes, sensors, and what have you, at 20% the speed of light. Why? You could have an interplanetary letter system like the Pony Express that connects all the planets within a matter of just a few days and would connect us to the stars within a matter of 20 years. Now, what's the catch? Well, the bottleneck is you have to have a laser bank of 800 megawatts of energy. That is a lot of laser power. You would have to build several laser systems, gigantic laser plants, energized by perhaps a nuclear power plant, and then the accuracy of aiming would have to be incredible. You would have to aim this beam of light so that these postage stamp chips do not miss their target trillions of miles into outer space. As you can see, most of the technology is off the shelf. We already have nuclear power plants, conventional power plants. We already have laser beams, powerful ones. It's just a matter of scaling it up and also creating the accuracy necessary to send this chip at 20% the speed of light out to trillions of miles toward the nearest star. So we're not there yet, but it's good to contemplate this because NASA is already taking plans to build perhaps the first Starship in the next century. NASA sponsored a forum about the 100-year Starship. It says that perhaps in 100 years, a Starship becomes a viable option, especially as we already know so much about the solar system. And then one last question, people say, well, why bother? I mean, we have so many problems here on the planet Earth. Well, as I've said before on exploration, realize that much of the technological progress in terms of computers, the internet, GPS, all of that, a lot of that came out of this space program. The space program demanded high technology that was miniaturized so that you could put it inside a space capsule. And that forced the miniaturization of transistors, and that in turn drives the internet, drives GPS, drives your cell phone, drives a multi-trillion-dollar economy because the space program forced scientists to miniaturize technology all the way down to the size of a small chip. Not to mention the fact that weather satellites, telecommunications satellites, they are indispensable for our society. As I mentioned before, years ago back in the 1960s, LBJ sent the Tyros weather satellite into orbit. Many people laughed and said it's simply a waste of money, millions of dollars, to send a weather satellite. And they said, well, if you want to know what the weather's like, simply go outside. Simply lick your finger, point it to the wind, and you know what the weather's like. Well, it turns out that as soon as the Tyros satellite went into orbit, one of the first things it photographed was a monster hurricane in the Gulf of Mexico headed toward Texas. For the first time in world history, we actually saw the fury of an entire hurricane from outer space. Well, I still remember LBJ had a press conference that very evening, and I still remember he said, today, the space program has paid for itself. Well, actually, he was wrong. The space program not only paid for itself, it paid for itself many times over. Think of the billions, trillions of dollars in our economy that depend upon weather satellites, depend upon the internet, depend upon the science and technology that's given to us by the space program. And speaking about the space program, some people say, well, isn't another benefit of the space program suspended animation? I mean, when we send astronauts to Mars or beyond, won't we have to freeze them, just like in the movie 2001? And if you could be frozen like that, why not freeze people who have terminal illnesses so they can be revived centuries from now? And by then, we'll have cured cancer. We'll have cured many of the diseases of today. Well, it sounds like a great deal, and according to rumor, several prominent individuals have already pledged their life to be frozen in liquid nitrogen when they die. But let's say a few things about the science, or lack thereof, of cryonics. First of all, cryonics is not a science at all. Nobody has ever been frozen solid and then thawed out. In fact, if you ever do such an experiment with a corpse, you probably wind up with a lot of dead tissue because of the formation of ice crystals. Ice crystals form between cells, inside cells. They rupture the cell wall during the freezing process. But certain fish and certain frogs can in fact be frozen alive because glucose is an antifreeze. However, that much glucose in our bodies is enough to kill us. And so here's the question. Can you freeze the human body and retard the formation of ice crystals by having antifreeze? So far, the answer is no. It turns out the antifreezes that have been tried, giving us what is called vitrification, turns out to be lethal. And so far, there is no way known to freeze the human body safely and then thaw the human body out later. It simply does not exist. Now, of course, at some point in the future, that technology may be created. I'm not saying that you can't ever do it. I'm just saying at the present time, you are wasting your money thinking that you can donate money to an organization that's going to freeze your body and then thaw it out after they cure cancer and any number of illnesses. Another question I often get in email is, how do we know really how far the stars are? I mean, no one has a meter stick. How do we know how far they are? Well, the close stars, we use parallax. And that is, if you move your head, for example, you know that close objects move a lot, but far away objects like mountains, they'd hardly move at all. And so when you move a telescope, you know that the farther you move the telescope, the closest stars move the farthest, and the farthest stars move the least. And using simple high school geometry, you can then calculate how far the stars are. Well, the farthest you can move a telescope is the diameter of the orbit of the Earth around the Sun. 93 million miles times 2. That is the diameter of the Earth's orbit. So you take a picture of the night sky in summertime, You then take a picture of the night sky in wintertime, compare the two photographs, and bingo. The stars that are closest to the Earth move more. The stars that are farther away move less because of parallax. Now, that works for close stars. For faraway stars, we have to use what are called variable stars, or yardsticks. It turns out that a star that is dim but very close to the Earth may be just as bright as a very bright star which is very far away from the Earth. So how do you tell the difference? You tell the difference by having a standard candle and knowing how intense it is. That standard candle is a variable star. It turns out that variable stars throughout the universe are pretty much the same. And therefore, the intensity of these variable stars, you can use that as a calibration. And so by looking at a variable star in our galaxy very close to the solar system and a faraway star farther away in our galaxy, you can therefore calculate the difference between the two by analyzing the intensity of starlight coming from the variable star, which is a standard candle. For stars that are even farther away than that, going all the way perhaps to the beginning of the universe, we have to use supernovae. There's a certain type of supernovae called type 1a supernovae, which flares up when one star gobbles up the hydrogen and nuclear fuel from its companion star. Now, exactly when that flare-up takes place can be calibrated, and again, it is a yardstick. It is uniform throughout the universe. And so by looking at an exploding star in a faraway galaxy, if it is a type 1a supernovae, we can use that as a standard candle to determine the distance to that galaxy. Now, we also have something called Hubble's law. Hubble was the great astronomer of the 20th century who showed that the farther a galaxy is from the Earth, the faster it's moving away. Farther means faster. Just like you have a balloon. If I put dots on a balloon, when two dots are very close to each other and I blow up the balloon, they don't move apart very quickly. But if two dots on a balloon are far apart, they move away very quickly. And so we think that the universe, therefore, is a bubble of some sort, and objects that are close to our galaxy don't move very fast, and galaxies that move very quickly are much farther away. And so we use that also as a check to calculate the distance to the stars. Also, earthquakes are in the news. I get emails about them, and they ask, well, we just had two big earthquakes, one in Italy that killed over 100 individuals, but also one in Myanmar, a bigger one, not a 6.2, but a 6.8 earthquake in Myanmar, which also caused extensive damage. And the question is there a link between these two earthquakes? They took place hours between each other. Is there a link? Well, yes and no. For the most part, there is no link. These earthquakes take place separated by thousands of miles. However, there is a very minor link between these two earthquakes. The Italian earthquake formed because Italy is one of the most earthquake-prone nations in Europe. It sits on top of two earthquake faults. Basically, you have the African fault in the southern part of Italy, and the Eurasian fault northward, and the two are colliding at the rate of about 2 inches per year, and that creates many of the monster earthquakes that have afflicted Italy. And in fact, in the 20th century, if you look it up in the history books, in the 20th century, over 100,000 Italians have been killed by many of the earthquakes that hit Italy over the centuries. Think about that, 100,000 just in the 20th century alone. Now, it turns out that the Myanmar earthquake had a similarity in the sense that there you're looking at the juncture between two tectonic plates. One is the Eurasian plate, the same plate that was involved with the Italian earthquake. But the other plate is the Indo-Australian plate. And again, the collision between those two plates is responsible for the 6.8 earthquake that hit Myanmar. So why was there so much damage in one but not so much in the other? Well, many reasons. Perhaps the primary reason is that the earthquake in Italy was a very shallow earthquake, very close to the surface of the Earth, only 6 miles beneath the surface of the Earth. Now, 6.2, as earthquakes go, is relatively speaking not such a great earthquake, but you saw pictures of the damage, extensive damage, especially to medieval buildings. Why? First, because the epicenter was only 6 miles beneath the surface, very close to the surface. And second, of course, because the buildings are very old, many of them dating back to the Middle Ages when they didn't have earthquake codes. Now, if you take a look at the Myanmar earthquake, it turns out the epicenter there was about 50 miles below the surface of the Earth. Therefore, even though the Myanmar earthquake had an earthquake of magnitude 6.8, it was simply not as dangerous as the earthquake that hit Italy because the epicenter of the shaking took place 50 miles beneath the surface. And I get another emails. People ask the question, even as Hillary Clinton and Donald Trump slug it out with all the presidential debates and all the press conferences they have, people seem to forget the fact that the government has been issuing warnings for this hurricane season. In fact, the latest government warning is that this hurricane season could be similar to the one that gave birth to Hurricane Sandy and Hurricane Katrina. But of course, no one's talking about it. Well, here's the question. How do we know this? Where does the power of a hurricane come from anyway? And let's say a few things about the mechanics of hurricanes. First of all, hurricanes start off as small tropical storms off the coast of Africa. That's right, Africa. Gentle breezes that form storms, and then they begin to go across the Atlantic Ocean. They go east to west across the Atlantic Ocean, and they don't pick up much steam until they hit the Caribbean. The Caribbean is where you have warm water, and that's where the energy of a hurricane comes from. It comes from warm water. Warm water causes hot air to rise. And as a consequence, because of the rising of hot air, the Earth spins beneath it, causing the hot air to twist a little bit, and that gives you the counterclockwise motion of the hurricane. That's called the Coriolis force. That's why hurricanes in the northern hemisphere go counterclockwise. Hurricanes in the southern hemisphere go clockwise. So think of it like a bowling ball. You roll the bowling ball down this long corridor, and that is the Atlantic Ocean. Then when you hit the Caribbean, that's when the power of the hurricane begins to manifest itself. And then it's like a bowling ball as it hits the pins. Most of the time, the bowling ball does not cause much damage. It simply washes up in an area that is not inhabited, washes out to sea, but the energy comes from the Caribbean. Once in a while, you get a strike. That is, the path of this hurricane is directly centered toward a major city. And that's what happened with Katrina. There have been many hurricanes just as powerful, if not more, than Katrina. But Katrina was different because, like a bowling ball, it was headed right for a strike. It was headed right for the city of New Orleans. And in fact, I saw a press conference once. It was one of the saddest press conferences I've ever seen in my life. The Army Corps of Engineers, which was supposed to protect the dikes and the levees against a monster hurricane, admitted they made a mistake. They had underestimated the intensity and frequency of monster hurricanes that could hit New Orleans and flood it, given the fact that a large portion of New Orleans is actually below sea level. That's right, below sea level. And so in some sense, it was only a matter of time before a monster earthquake, like a bowling ball, hits a strike and is headed right toward a major city like New Orleans. So for this season, I think we should have to be very careful, given the fact that two things are happening. One, we have global warming, which also causes the surface temperature of the waters to rise. Not to mention computer simulations showing that the energy of hurricanes could be comparable to the energy of Katrina and also Hurricane Sandy. Well, I'm afraid that's it for the first part of Exploration. And in the second half of Exploration, we are going to go into outer space. Outer space with an astronaut who's actually been up there. And the question is, one day, are we going to go to Mars? One day, will we ever venture to the nearest star? That is Proxima Centauri, part of the Alpha Centauri star system. And the question is, well, what are we going to find if one day we send our astronauts that far into outer space? So our special guest today is astronaut Tom Jones, an astronaut who has flown with the space shuttle several times. And we're going to talk about what it's like to be into outer space and to commune with the universe. Welcome. Once again, this is Dr. Michio Kaku, Professor of Theoretical Physics at the City College and the Graduate Center of the City University of New York, and this is the second half of Exploration. In the first half of Exploration, we summarize some of the questions that I get in email, including a lot of questions about the discovery of a planet, the closest planet to the Earth, that is Earth-like, Proxima B. And then the next question is, what would it take to send an astronaut to that planet? Well, it would take about 70,000 years with a conventional Saturn rocket to go from the Earth to Proxima B, 4.2 light years from the planet Earth. That's too long. We need a new kind of propulsion system. But with us today to talk about what it's like to go into outer space is Tom Jones, a pilot with the Shuttle program, which of course has now been canceled. And he'll talk to us about, well, what it's like to experience weightlessness, what it's like to live in outer space, given the fact that a simple mission to Mars would take upwards of perhaps 2 years, 9 months to go to Mars, several months to do reconnaissance and do scientific experiments, and another 9 months to come back from the red planet. And just remember that the world's record for a continuous nonstop flight into outer space is just a little bit over a year. And that's the world's record set by Commander Polyakov of Russia. And so you can understand the daunting challenge facing our astronauts. And remember that the space shuttle simply spun around the planet Earth in near-Earth orbit. To go to Mars, you have to go through the Van Allen radiation belt. You have to withstand micrometeorite impacts, solar flares, X-rays, gamma rays from outer space. You name it. You have to experience it and understand the dangers involved if you are on a mission to Mars. And NASA says in 25, perhaps 35 years, we'll be sending a manned mission to Mars. Once again, our special guest is Tom Jones, a space shuttle pilot. And we'll talk today about, well, what it's like to go into outer space, to experience weightlessness, to experience the joys of leaving the planet Earth. The first question for you, Dr. Jones, is, as a youth, how did you first get interested in exploration and the space program?
It's easy to remember for me. My grandmother was a big reader, and so she went down to the five and dime store and bought on the remnant table a book called Spaceflight, The Coming Exploration of the Universe. It was one of these little golden books of knowledge that you could get back in the 1960s. And so I was 5, and she gave me this book, and it was filled with wonderful illustrations, paintings of what spaceflight might be like. There were no photos because no one had gone into space yet, but that really captured my imagination. These astronauts and spaceships were fascinating subjects to me, so I began to read more about those on trips to the library, and very quickly got fascinated with the subject of space science and astronomy. When I was 12, my parents got our family our first telescope, and I became the sole operator of it. It was tough to get other people to let other people use it, but I had it out a lot in suburban Baltimore. And along with the fact that they were building rockets in my hometown as part of the Gemini program in the middle 60s, I think all of these things combined to make astronautics and astronomy a very favorite subject of mine, which I just devoured in school and at the library.
And you went to the United States Air Force Academy. Why did you go there, and did you have in the back of your mind this career path that would take you into outer space?
Well, certainly by the age of 10, I was aware of the job of astronaut and the fact that it was a reality and that they were building rockets in my hometown. And I said, well, I'd like to ride a machine like that. someday. And during the Apollo program, as we watched the first run-ups to the moon landings, I was aware that test pilots were the ones who were selected to be astronauts. So if I wanted to do the job, I certainly had to become a test pilot. And you've got to go through a military flight training program, and I chose the Air Force. So the Air Force Academy seemed to me the best place that was focused on flying in the country, and that's why I tried to enroll there. By the time I was in college, the moon landings were just finishing, and so it was very clear that I still wanted to do this, and I thought that was a great jump on the program, getting into flight school, becoming an Air Force pilot, and then becoming a test pilot.
And I understand that you flew missions on B-52 bombers for the Strategic Air Command. Could you elaborate?
Well, after a year of pilot training after graduation, I got a basic science degree at the Air Force Academy. I knew I was going to be flying for a while and then try to get into test pilot school. So my first assignment after pilot training was to go to Strategic Air Command, which was an outfit that was involved in nuclear deterrence. And my mission as a B-52 crew member, a co-pilot, and then an aircraft commander was to sit alert duty out at the base. About once every 3 weeks, I would live for an entire week out at the base, trying to make sure that the Russians would always fear a counterattack if they tried to do a surprise attack on the U.S. So we trained for the nuclear delivery mission, a doomsday mission. And it was quite a strange existence. Every third week, you'd be waiting for the horn to blow, signaling a Russian attack, and then you'd jump into your planes and taxi out as fast as you could and take off. That's what we trained for. And fortunately, nobody ever shot at me, and the Cold War wound down to its eventual conclusion. While I was doing that, though, NASA brought along the space shuttle and changed the rules on how you could become an astronaut.
Now, many people who watched the movie, Top Gun with Tom Cruise, have dreamed about dogfights up there in the wild blue yonder. However, you went for a PhD in planetary sciences. So how did that come about?
Well, to tell you the truth, I was in the Air Force and sitting alert duty, and I remember clearly being out there on the base during one of those weeks of duty and watching the miniseries Cosmos by Carl Sagan. And this was a man and a television production that really captured my imagination. And I said, here's a guy who's doing this for a career, the thing that I've loved to study and read about all these years. And now that NASA is looking for scientists and engineers, maybe I can become a space scientist, and maybe that would be an alternate path. I knew that test piloting would be a tough assignment to get. It was very competitive in the Air Force, and especially for bomber pilots who weren't widely needed at that time. So after watching Cosmos and reading some more books about that particular profession, I decided I'd go back to graduate school and see if I could become a practicing research scientist.
Now, a lot of people ask the question, if I want to become an astronaut, what do I do? Do I send a postcard to NASA saying, sign me up? What is the career path? What is the process by which somebody out there can realize a dream of going into outer space?
Well, it's easier today with the Internet. You can get on the Internet and read all about astronaut selection at nasa.gov, nasa.gov, their website, and search for astronaut selection. But back then, you just wrote a letter to the Johnson Space Center in Houston where the astronauts train, and I got a reply back from the selection office, and they informed me about the basic qualifications. You have to send in an application, which includes a big civil service exam and a lot of paperwork to fill out, as well as a medical exam. And you just send in that application, they keep it on file, and then every time that they select a new group of astronauts, they'll notify you to see whether you're still interested in applying. And so I started that process in 1986.
Now, 1986 was also a watershed year because that's when the Space Shuttle Challenger blew up on international television, a very sobering event. 7 astronauts tragically lost their lives in that accident. And we sometimes forget that going into outer space is not a Sunday picnic, that about 1% of the time there is booster rocket failure and major malfunction of rockets. So was that sobering? How did that impact on you?
Oh, it was terrible. I was watching that accident. I was watching with the launch of that mission with Krista McAuliffe, the first school teacher to go into space, with a bunch of school students, elementary school students at the University of Arizona, where I was a graduate student. And the catastrophe unfolded before us on this big screen TV. And, you know, you had to try to make some sense of it for the kids and tell the kids that there was no hope that they'd gotten out. And it was a terrible emotional blow. Next door at the Lunar and Planetary Lab where I was studying, everyone was completely floored, devastated by this emotionally, even though most of the people were involved in planetary science and astronomy and robotic missions, they knew how serious this was for the future of space travel and exploration in general. So it was a real body blow. I had met the commander of that mission about a year before, and he'd encouraged me to apply to become an astronaut. He was a very motivated guy who was clear about his mission, and it was infectious. It motivated me to follow in his footsteps. And after his death, Dick Scobie, I decided that, well, he must have really believed in this to risk his life in such a way. And I knew that my desire to do it was very strong, and I thought if people like that I look up to are willing to risk their lives, then I still think I could find the courage to do the same thing. And I talked it over with my wife before I began applying.
Now, you're a former test pilot, and you know when you go into that cockpit that you're putting your life on the line. You know that unlike a civilian, which wants lots of life insurance and assurances there's no problem, you know you're putting your life on the line when you go into a jet airplane. Now, when you become an astronaut, are the astronauts also told the same thing? We have civilians going into outer space. We have politicians and multimillionaires now going into outer space. Are they really mentally prepared for the fact that, well, like I mentioned, roughly 1% of the time there is catastrophic failure?
Well, we're certainly aware of the risks. As a pilot, I didn't become a test pilot. I actually left the Air Force after just flying bombers because I wanted to pursue this science path. But I knew that the professionals involved in flying the shuttle were aware of the risks. Of course, Scobie certainly was. And I decided that there must be a recognition among all the crew members that what they're doing must register on them as being so worthwhile that they're willing to risk their physical safety, even their lives, to accomplish these missions. And when I got into the astronaut corps in 1990, I found that to be true, that people were thinking of this as a long-term program of exploration. They figured that the benefits they'd bring back from each mission would be building blocks that future explorers would use to return to the moon, get to the asteroids and Mars. So we all viewed this as a continuum, and each little contribution that we made was worth the risk of our lives. Now, the shuttle's a pretty safe machine. Even though it's had 2 terrible accidents, it's one of the most reliable rockets that's out there. So you can always tell yourself that it's not going to happen to you, but you must recognize that it's a finite possibility that each mission's got, 1 in a couple of hundred chances of leading to a catastrophe.
Okay, now let's get into the guts of your book. That is the training of an astronaut and what it's like there to orbit the Earth and look down from outer space. First of all, the training. Let's talk about going into swimming pools, going into 1,000 horsepower centrifuges, going into the vomit comet. What is the grueling regimen that astronaut training entails?
Well, to begin with, it's much like a college curriculum of investigating the basics of spaceflight. So you bring in all these people who are test pilots and scientists and engineers, and they have varied backgrounds, but everyone's capable of learning. And so essentially it's a graduate course in spaceflight and its fundamentals and the systems that allow us to survive and work up there, the space shuttle in this case. So it's a year of astronaut basic training. And you start in a classroom, read a lot of books, get a lot of lectures. So that's very familiar to most of us. And yet it moves very quickly into simulator training, where you're actually flipping switches, reading checklists, working as a team to put into practice what you've learned in the classroom. And there are also a lot of ancillary training experiences that are quite fun, even though they're very serious in mind, like survival training. What do you do if you bail out of a jet or out of a shuttle and you come down in some distant location where you've got to await rescue? So we had water and land survival training. We also, as you say, rode the centrifuge to prepare us for the accelerations of launch, scuba training to prepare us for underwater training in a spacesuit to simulate free fall, and finally that ride on the vomit comet that everybody looks forward to, where you get 20-second doses of free fall as the airplane rides this roller coaster path through the sky. And that's both exuberant and exhilarating, and then finally in the end it's an endurance contest to see if you can keep your stomach and your mind together while this airplane does these gyrations. But it's great to experience free fall.
Now, people who saw the movie Apollo 13 saw Tom Hanks floating for what seemed like forever, and people said, well, how'd they do that? There's no room for wires in that tiny little capsule. How'd they get Tom Hanks to float like that? And as you mentioned, it was this airplane called the Vomit Comet, and there's a reason for that. People throw up. Is that right?
Well, some do. Most people get a little queasy after the end of an hour and a half on that plane, where you do 40 up and down roller coaster cycles to give you those cycles of weightlessness that last 20 or 25 seconds. It's very aggravating to be in free fall for 25 seconds and then be slammed to the floor with 2 times the force of gravity as you pull out. And when you do that over and over, it tends to tumble your gyros and lead to nausea. I found that I never really got aggressively sick up there, but I certainly felt after the end of those 40 parabolas that I was ready to walk wobbly off the airplane and go sit down quietly for a while.
And let's talk about weightlessness. Weightlessness is the state of free fall. That is, if you're in an elevator and someone cuts the wire of the elevator, God forbid, you are in free fall and you are weightless because the floor of the elevator falls at the same rate that you do, giving you the illusion that there's no gravity. Of course, there's gravity. It's pulling you to the floor, but the floor is falling at the same rate as you. Same thing with the vomit comet. You're essentially being hurled like a rock into the atmosphere and you are in free fall. So the question is, if you're in free fall, that sensation is a sensation of dying. That is, you're falling off a skyscraper. So is that the sensation that you have, that you're thrown like a rock into the atmosphere in the vomit comet? Is a sensation like the sensation that you're dying?
Well, fortunately, your body is pretty easily fooled. Your mind is fooled because you're in a cabin of an aircraft or you're in the cabin of a space shuttle, and you can't tell that you're being hurtled through the atmosphere or around a planet at hundreds or thousands of miles per hour as you fall, either on this roller coaster parabola or in an orbit around the Earth. So to you, your surroundings are falling with you. They all appear motionless. That's your frame of reference. And so you just appear to be floating. And so it's rather a gentle feeling. You don't feel any motion of high speed or even standing on the edge of a precipice and leaping off. So it's pretty easy to get used to. It's just a gentle lifting or a floating feeling, and it's nice to be able to move with just a fingertip push against the walls. And I find it's something that you actually forget about after a couple of days.
Now, you spent 52 days in Earth orbit during the 11 years you were in the astronaut program. So everyone wants to know, if you're up there for not just 20 seconds, but for days on end, how do you do very simple bodily functions? Like, for example, eating. How do you eat when your food floats in front of you? How do you drink if water will simply float to the ceiling? And what the question everyone wants to know is, how do you go to the bathroom?
Well, all of those subjects I try to explore in skywalking to give you that personal experience of being in there. The eating, fortunately, is almost a non-issue. All of your swallowing and digestive functions seem to work just fine with the peristalsis that moves things through your digestive tract at work. Doesn't need gravity to function. You do have to eat these foods out of a pouch and drink liquids from a pouch with a straw inserted so that food and debris and globules of liquid don't float around the cabin and mess up the systems up there. So it's rather tedious after a while that you have to eat one package at a time. You don't get to sample 3 or 4 dishes at once. You've got to eat in a serial fashion, and it almost becomes perfunctory after a week of the novelty wearing off. So, but it's aside from a little bit of extra time and care required, it's actually quite easy to eat and drink. And I still enjoyed the varied menu that we had available to us, even though the foods aren't fresh. They're at least freeze-dried or irradiated or thermostabilized, so they retain some good flavors. Now, the bathroom question. Down here on the ground, gravity makes everything go where it's supposed to. And as I write in the pages of Skywalking up there, you've got some special training to use because we use air instead of gravity to make things go where they're supposed to. Liquid down a suction hose where each crew member uses a personal funnel to guide the liquid into the tube. And for solid waste, it's blown into a storage tank underneath the commode seat. And then the clever thing about it is that the solid waste tank, while it's not in use, is exposed to a vacuum. So the solid waste is sterilized and dehydrated, so the next time it's used, there's no odor or chance of a pathogen getting back into the cabin. It's quite clever. And while it takes longer to use the system than on Earth, it actually functions quite well.
Well, according to the book, The Right Stuff by Tom Wolfe, when our first astronaut, Alan Shepard, was sent into a suborbital trajectory, he had to go to the bathroom. He told Mission Control he had to go to the bathroom, and Mission Control vetoed it. And so they sent him into outer space where he essentially urinated in outer space. Now, that is not a good thing to do, right? Because if you have liquid inside your spacesuit and you are weightless, it could be a mess, right?
Well, it certainly was a mess, and I'm sure he was quite a smelly guy when he came back and got out of the suit. But he survived just fine, and that's because of spacesuit design. They don't put any electronics generally inside an oxygen-filled suit unless there be an ignition source that could lead to a fire. So the inside of a spacesuit tends to be a quite benign place, and the liquid was just a little bit of mess. Fortunately, on the space shuttle, we deal with free fall inside a spacesuit by using diapers, large, absorbent, adult-sized diapers that can take care of that eventuality. And, the space shuttle itself, provides a means to get out of the suit right after you arrive in orbit, and you don't have to put the suit back on until re-entry. So then you can use the bathroom facilities that we just discussed. So we're a long way from the right stuff now, and people seem to be able to deal with this quite easily.
Okay, now, what is it like spiritually and emotionally to be in orbit, to look down on the planet Earth as you are in a spacewalk? Suspended, orbiting the Earth, suspended in mid-flight with this little cable that connects you to the mothercraft. What is it like to look back at the Earth?
Well, Michio, this was a great experience. I had been dreaming about spaceflight since I was 10, and here I was, 39 years old on my first mission, and as I write in Skywalking, I got to orbit. I was so busy with my initial jobs that it was about an hour before I actually had a moment to look out the window. And I'll never forget that first impression of the Earth. I was looking out on the night side of Earth, and instead of stars, I saw this big round space or gap where stars should have been. That was the dark side of our planet. But on the very edge, the limb of the Earth, was a gentle band of robin's egg blue light that was growing in intensity and widening along the horizon of the Earth, and that was the coming sunrise. And this beautiful, delicate blue, and the fact that I was finally looking back at my planet after waiting for almost 3 decades to get there brought tears to my eyes with the realization that I had finally arrived at that moment in time and space. And, they were tears of gratitude to God for sending me up there and giving me the chance to do this, and they were just tears of appreciation at the beauty that I was seeing. And throughout my experiences in space on the other 3 missions I flew, the view of the Earth never became boring, or I never became blasé about it. It was always riveting. I had to tear myself away from the windows to go to work because it's always such a lovely sight and so attractive to a human being to gaze on our own world.
And do you also get a sense of the fragility of life? First of all, the atmosphere is extremely thin, and yet it's like the skin of an apple, and yet it creates life on the planet Earth, not to mention the fact that the Earth is suspended in this rather hostile environment of cosmic rays and potential meteor impacts. So do you get a feeling of the fragility of humanity that we are, quote-unquote, on Spaceship Earth?
You certainly get a sense that the Earth is a varied and delicate place. You see immense variety in color and in texture as you travel around the planet once every 90 minutes. Looking at the Earth's horizon, you can see this thin blanket of the atmosphere. You can look down at night and watch meteors burning up in it below you, and you can see the air glow layer high in the atmosphere against the dark night full of stars. So it's aesthetically beautiful, and you're aware of how thin that envelope of air is in particular. I found that you wanted to get to these thousands of places on Earth that you could see, that the rainforest, the glaciers, the high mountain peaks, the river valleys. You wanted to go personally to all of these places to learn more about the planet, and yet you realize as a human being you're never going to live long enough to go to all of these places that you've seen from orbit. I felt a great attraction and sense of longing in my heart to be part of Earth, and I felt separated from it to some extent, especially thinking that I was half a world away from my family most of the time. But generally, I had this great attraction for this lovely planet of ours, and I can't imagine what the Apollo astronauts must have experienced traveling 1,000 miles farther away in space than I did. And it was so strong for me, I'm sure that they must have had a great longing to get back.
Okay, now let's talk about the downside of being in outer space. For example, the Russians set the world's record for being in outer space on one mission, being lofted into space for over a year. And when that cosmonaut came back down to Earth, he could barely crawl. He was almost like a worm. The atrophy of the muscles was so great that he could not stand up. And so let's talk about the fact that when you're in space, you have enormous muscle and bone loss.
Short-term space flight doesn't present many problems. We exercised every couple of days while we were in space. The longest trip I had was 18 days. And so if you do a medium amount of exercise for an hour every other day, you're going to keep your heart, lungs, and muscles in good enough shape to do any physical task that's required and also to withstand re-entry. And then you can sort of stagger off the space shuttle and get your land legs under you just as you were coming back from a long sea voyage. And within about a half an hour, you can walk under your own steam with no great worries. You feel heavy at first when you come back to Earth, that passes in about an hour. The longest effect that I felt was about 3 days of lacking a fine sense of motor balance. So I couldn't bend over from the waist and pick up a penny on the floor. That would have just toppled me over. I had to wait until my brain became used to using those inner ear balance organs again, and it took about 3 days for those to come back online. Now, for space station astronauts like my friend Bill MacArthur, who's headed back to Earth on April 8th here, he's been up there for more than 6 months, and he's been exercising every day for 90 minutes. He's been using both a treadmill and an exercise bike and a resistive exercise device that allows him to do the equivalent of lifting weights up there. And by combining those forms of exercise, his muscle and cardiac health will be in pretty good shape when he comes home. So I think he'll be able to walk within about an hour. He's got the benefit of a lot of experience since that Russian mission 16 or 17 years ago. He'll be able to be more mobile when he comes back. He will have, however, some loss of calcium from his skeleton. He's lost some bone mass. Some of that will recover back on Earth. He'll probably have a permanent deficit of a few percent. And, of course, we don't know the long-term repercussions of that. So while he's going to get some professional physical rehabilitation, I think he'll have no short-term ill effects, and it'll only be in the later decades of his life that he finds out whether he's got skeletal weakening that's of any consequence. It doesn't appear to be a long-term effect for these 6-month space station missions. But as you understand, Mars missions are an open question.
Well, I'm afraid that's it for exploration. Once again, this is Dr. Michio Kaku, Professor of Theoretical Physics at the City College and the Graduate Center of the City University of New York. Good day for exploration.